In this video, we further examine the behavior of circuits that contains energy storing elements such as the capacitors and inductors. Um, in particular, we will determine the initial conditions of RC and RL circuits that are essential in finding their complete responses. At any given time, the circuit has a state, which is nothing but the status of the voltages across and the currents through the different elements of the circuit. The state of the circuit can change depending what and when changes occurs on that circuit. Here we have a simple circuit where a switch closes at t equals 0. Prior to the closure of the switch, uh, the state of the circuit is that the current is 0. And then at t equals 0, we introduce a voltage to the circuit. So at t equals 0, a change happens on the circuit, and that is the application of a 50-volt source to the circuit. Consequently, the state of the circuit will change because of the introduction of that change, which results into a current that flows through the resistive elements. And uh, the or development of the voltage across those elements. Take note that time t equals 0 can be any time, like 7 o'clock in the morning. So therefore, before 7 a.m., that means that t there has a negative value, and after 7 a.m., uh, t has a positive value, and exactly 7 a.m., t it has a 0 value. Let's say I want to plot the magnitude of the voltage at any given time. Take note that this circuit has its switch closed at time t equals 0. So meaning the time before 0 has a value of negative on the left side and positive on the right side. So this is the plot of the current. So we see that the current before t equals 0 is a 0, and then at t equals 0, it jumps to 30 volts. So we can see that the voltage V2 is 0 before t equals 0 and jumps to a value of 30 volts at t equals 0 and stays on that value all throughout. We can also plot the current that flows through the resistive elements. This is the current I, and this is the plot. So the current is 0 before t equals 0 and also jumps at a value of 1 ampere and stays on that value regardless of time. Take note that we have plotted I side by side with V2. Let's say I replace the 30 ohm resistor with a capacitor of unknown value, and I again plot the voltage V2 and I. Okay, so here is the plot. So take note that V2 is 0 before the switch is closed or before t equals 0, and exactly at t equals 0 it is still 0, and from there it starts to increase until it becomes 50 volts. Okay, so take note that the value of V2 does not exceed 50 volts and becomes constant as time progresses. We can also plot the current. So the current stays at 0 before t equals 0, and then at t equals 0, it suddenly increases to 2.5 amperes, and from there it starts to decrease towards 0 and stays 0 as time increases. Take note that we have slightly written v sub 2 and I differently. So v sub 2 now is a function of time, and I is also a function of time. It's because these quantities now varies with time, unlike these quantities here. Now let's evaluate the state of the circuits. So we have two circuits. So for this circuit here, so during this time period, the state there is a steady state because the voltages and the currents are constant. And in fact, they are zero because there is no source yet before t equals 0. And then during this period, it is also steady state because the voltages and currents are also constants. So the voltage is 30 volts and the current is 1 ampere, and it is a constant regardless of time. There is no transient state because when we close the switch at t equals 0, the voltages and currents immediately go to a constant value. On the other hand, in this circuit, during this time period, it is a steady state, and during this period, it is also steady state because the currents and voltages are constant. So, for example, V sub 2 is 50 volts, and the current there is 0. Now, this time period here is the transient state because the voltages and currents are all varying with time. Now, how long is this period depends really on the values of the elements. So, like for example, the capacitance of the capacitor and the resistance. So, in a circuit containing energy storing elements, what happens is that usually the circuit is in steady state. Then you introduce a change in the circuit, a transient state will uh, occur, but eventually that circuit will again go to a new steady state. In dealing with circuits containing energy storing elements, it is always necessary to know the initial conditions of a particular circuit. So the initial condition is the state of the circuit before any changes to the circuit is applied. But there is more to the initial condition of a circuit. In fact, we could classify the initial condition in three stages. That is the condition of the circuit just before the application of changes, at the moment the changes are applied, and just after the changes are applied. So what do we mean by this? So let's say we have here a circuit again. So our circuit is steady state before t equals 0, and then after the application of the voltage, it underwent a transient state, but eventually it returns to a new steady state. So what is the initial condition of the circuit? So let's, for example, take uh, the voltage V2. So we know this voltage to be a function of time. Okay. So just before t equals 0, we know the voltage to be 0 here, right? So therefore, just before t equals 0, our V2 would be equals to 0 volts. Okay. Just or exactly t equals 0. So this is the point here. V2 is still 0. And just after t equals 0, so it is somewhere here, we still get V2 equals 0, right? Now for the current, just before t equals 0, the current um, through the capacitor or through the circuit, which is also, so this is voltage and current. So the current there is also equals to 0. Then exactly t equals 0, our voltage, okay, so our current, I mean, take note the current here is 0, it's not shown. And then it jumps at t equals 0, it jumps to 2.5 amperes, so meaning at exactly t equals 0, current abruptly changes to 2.5 amperes. And just after t equals 0, so it is somewhere here, it is somewhere here, okay. So we get there I still equals to 2.5 amperes. So that is what we mean by the condition of the circuit before, uh, during, and just after the changes are applied. Regardless in what time you are, the KCL and KVL uh, still applies. So what do you mean by that? So for example, um, at t before 0, so let's say t equals negative 1 second, you should be able to apply the KVL equation. Well, our switch is open, so therefore we don't have a complete circuit, so we couldn't write an equation involving the current I. Now let's say t equals exactly 0 seconds. So the circuit is complete. We could write our equation. So that is minus 50 volts plus 200 times the current I at t equals 0 plus the voltage across the capacitor. Uh, Let me just write it as V sub 2. So V sub 2 at t equals 0. Okay. For t equals, let's say, 1 second, that is after the changes are applied. So the circuit could be undergoing a transient. Still, a KVL should apply. Okay, so that if we write the KVL, that should give us minus 50. So we start here, plus 200 times I at t equals 1 second, then plus v sub 2 at 1 second equals 0. Okay, so the Kirchhoff's laws still apply regardless in what time you are analyzing the circuit. For a series RC circuit where we're trying to get the voltage V sub C across the capacitor, we can use the following conventions to show the initial conditions of the voltage. So for the voltage across the capacitor just before t equals 0, we can write it this way. Okay? So it's V sub C uh, at t equals 0, a minus symbol on the upper right of 0. For t exactly equals 0, the usual we use V sub C at t equals 0. And for the voltage just after t equals 0, we can write this where the 0, uh, a symbol, a positive symbol on the upper right of 0. Hence, for this particular circuit, we have the voltage V sub C just before t equals 0 equals 0 volts because there's no current yet. At exactly t equals 0, V sub C equals 0 volts. So it's still 0 because the voltage cannot change abruptly. And just after t equals 0, it is still a 0. Okay, so there are 3 points here before t equals 0, exactly t equals 0, and just after. Okay. For series RC, the voltage across the capacitor, the magnitude of the voltage across the capacitor are always the same just before, during, and just after the change is applied. Now, the time during the changes are applied may not be time t equals 0. So let's say the time there is t sub 0. So in general, we could write this one as this one. So where again t sub 0 is the time where changes are applied. Okay. Now take note, the voltage across the capacitor cannot change abruptly. So as shown on the last slide, uh, if we apply changes to the circuit, the voltage across a capacitor cannot jump from a certain value to a new value at an instant. Okay, so it cannot change abruptly, or that would mean a very, very large current. Okay, so that is not possible. So for the current, uh, if we'll get the initial conditions at t just before t equals 0, our current is 0 at exactly t equals 0. It will jump to 2.5, and just after t equals 0, it is still 2.5 amperes. So the current through a capacitor can change abruptly. So as we can see here in the graph, when the changes were applied, when the voltage was applied, the current immediately jumps from 0 to 2.5 in no time. So it changed abruptly. That is possible for a capacitor. What is not possible is the voltage. When a voltage across a capacitor becomes constant, so this voltage, when this becomes constant, the current becomes 0 because, take note, I through the capacitor is C dVc dt. Okay, so if V sub C is a constant, so this one is a constant. So this one, getting the derivative will give you 0. So that will make your I 0. And if the current through a capacitor is 0, you could interpret that capacitor as an open circuit. So it behaves like an open circuit. Now let's go to the initial condition of a series RL circuit. So we replace the capacitor with an inductor, and again we assume that there's no voltage applied before t equals 0. Then at t equals 0, we apply the voltage, and it will give you a current that will look like this one. Okay, so we will be deriving these curves as we go along. So in a series RL, the current does not change abruptly. So from 0, it gradually increases to a constant value until it reaches a steady state value here, somewhere here. So again, this is the steady state. This is a steady state period. This is a transient period, and this could be steady state period again. So what are the initial conditions of the voltage and the current through the inductor? So let us take first the current through the inductor. So at t just before 0, we notice that our current is 0. At exactly t equals 0, our current is still 0. And just after t equals 0, our current is still 0. So right here. For the current through the inductor, the values of the current before, during, and after the changes are applied must be equal. Okay. Now, in general, again, the changes may might be applied on some other time other than 0. So to generalize, we can write it this way. So the current to an inductor cannot change abruptly, because if that happens, that means that we have a very large voltage across the inductor, because the voltage there is LDI dt. So if current changes abruptly, that means you have an infinite slope, and that will give you a very large voltage. For the initial condition of the voltage across the inductor, at time before t equals 0, you will get there a value that is equals to 0. Then at exactly t equals 0, the voltage jumps to 50 volts. So we get 50, and just after uh, the changes are applied, uh, we still get a voltage that is equals to 50. So for the voltage across an inductor, it can change abruptly, but the current cannot. When the current through an inductor becomes a constant, that will give us a voltage that is 0, because, as we've said, um, Voltage across the inductor is L di dt. So if I is a constant, this should be equals to 0, and that should give us VL equals 0. And if the voltage is 0, that would mean this element is like a short circuit, right? So that is the behavior of the inductor when the voltage becomes 0. So in this video, we showed that there are two possible states for a network that contains energy storing elements. These are the transient state and the steady state. Transient state occurs when networks are subjected to changes. These changes could be the closing or opening of the switches. Networks always go to steady state over time when no further changes are introduced to that network.